My name is Audris Mihailovs, and I will be talking about Skylar, a compact and agile air-ground omnidirectional vehicle. Skywalker robot is that beauty on the right, but before we get to the good part, some background is required. We will be looking at two types of robots, unmanned ground vehicles or UGVs, and drones, but of course there are a lot of other options as well. Drones are becoming increasingly popular, and they are widely used in fields such as photography, exploration in unknown scenarios including search and rescue, package delivery, and many more. The drawback for all drones is the battery life, because it constantly has to fight gravity and that takes a lot of power. But if you add a lot of batteries, it increases the weight and the problem still remains. UGV or unmanned ground vehicles are pretty similar to drones, maybe putting slightly more focus on the military and transportation, but they are useful in other fields as well. But luckily for UGVs, they don't really need to fight the gravity, because the biggest force that works against them is friction, which highly improves the battery life of our robot. But every great thing has a roadblock, and this one is a roadblock. Thus, we come to our amazing equation. Plan is to take the best of both worlds without either of the problems. Or at least try to. That we have air-ground vehicles. These type of vehicles try to utilize the best of both worlds. And as you can see, there are a lot of options. From drones encapsulated in a wheel-like structure, as you can see in the example A, to even robots with legs, which have example D and K. All of these robots usually fall into three categories, which are passive wheel-based, vehicle moves only using propellers, active wheel-based, wheels have an additional motor, and leg-based. Even though these robots are better in ways than their single category counterparts, all of these usually have one or many of the following problems: low trajectory tracking ability, slow mode switching, tight kinetic constraints, or complicated mechanisms. But the scientists behind this paper believe that they have managed to solve most of the problems that usually occur, and the special things that the Skywalker has are a passive omnidirectional wheel. It's actually the same wheel that luggage cases or shopping carts have. Propeller protectors, because the wheel is passive, the ground part still relies on the propulsion of the propellers, thus ensuring they don't break is important, and an onboard computer, which by itself is not anything special, but scientists created an advanced propulsion control system which has a lot of beautiful math behind it. But feel free to read about that more in the paper. Here, you can see how the robot executed an H-shaped ground test, and it reached the speeds of 4.5 meters per second, and maximum acceleration was 4.3 meters per second, while the average velocity was around 3.3 meters per second. But the very important part of this is that the root mean square error between the reference and estimate trajectory is 0.08 meters, which means it was very good at executing trajectories accurately. More advanced experiment where it's possible to observe the air-to-ground hybrid trajectory, where it switches between driving on the ground and flying, and happens twice. And it does this very smoothly, as you can see. Experiment that you saw, here are the graphs that show you the information. The red circles show you where the mode switching happens, and the maximum velocity for this was 5 meters per second, maximum acceleration for the experiment was 4.6 meters per second, and the average velocity was 3.1 meters per second, while still having the RMSE at 0.129 meters, which means it did it quite accurately. Another experiment that the scientists did was with the yaw angles. On the top video you can see when the yaw angle was set to 0, or essentially fixed. Middle video shows when the yaw angle is set in the direction of the velocity, while the bottom video shows it fixed at pi. You might have some flashbacks from our labs. These type of tests show how well it can be used for different application because the RMSE was 0.92 meters, 0.128 meters, and 0.125 meters respectively. In conclusion, here you can see how the Skywalker compared to other robots in the categories, and these categories were such as motion ability, switching speed, kinetic constraints, structure simplicity, and energy efficiency. In all cases, it was the best or one of the best in the category. Of course, the sample size is small because these were the only ones the scientists could get their hands on. Although I would like to say that all of this has to be taken with a grain of salt, because these type of tests only show how effective a concept can theoretically be, but if it would be used in practical and real life scenarios, I believe that there would be a lot of problems that would arise. And with that, thank you for the attention and may the force be with you.